Hello everyone, my name is Enhao Zhang, a PhD student from University of Washington. Today I will present Equivocal, a system that synthesizes queries for compositional video events from limited user interactions. Video data management systems have received increasing attention from the database community in recent years because it is getting much easier to collect and store large amounts of video data, and also the advances in computer vision has brought up many new techniques to help people understand video contents. And one interesting problem in video analytics is to study how to enable users in expressing complex queries from video data, and consider a traffic video analytics application. A traffic engineer may want to study road hazards involving car and motorcycle interactions, such as a motorcycle swerving abruptly in front of a turning car. And similarly, in the ecology field, scientists have collected a large amount of video data to study complex animal behaviors. And so how could we find complex videos, complex events from videos? And one option is to use a machine learning model to identify a target event from videos. And there are already many computer vision models that can detect common objects and common activities. However, a specific classifier that can detect the desired user events directly without retraining is unlikely to exist. And if the user wants to train a custom model, they have to go through a tedious and time-consuming labeling process. And from the database community, there are also many great systems that support such use cases. These systems allow users to express a query either by sketches or by writing Python programs. But if you think about that, it is actually hard to express such queries in the first place. It means the user has to be familiar with the language in order to express such queries. So to address these challenges, we propose a new system called Equivocal. And the main idea of Equivocal is that we want to synthesize queries on users' behalf. This means that we don't ask users to express a declarative query manually. We don't ask them to provide a large number of labeled examples in order to train a custom model. And what Equivocal does is to synthesize queries automatically for the user and from only a few labeled examples. And let's see how Equivocal works. So the user comes to the system with an event of interest in mind. And remember that the user never has to write down their event. The user has to provide a few labeled examples to the system, and eventually Equivocal will return some synthesized queries. And in order to synthesize queries, Equivocal also needs a set of user-defined functions, and these functions are used to extract semantic information from video data. And these functions only need to be predefined ones, and even like and they can even be prepared by the system. And Equivocal also wants to minimize user efforts, so the system doesn't ask user to provide all examples in advance, and instead we do it iteratively by asking users for more labels during the query synthesis process. And by the end, the user could use those synthesized queries over the unseen videos to find more matching video segments. Equivocal needs to solve a number of technical challenges. First, it should minimize user efforts by using a smaller number of labeled examples. It should synthesize queries efficiently, so the query search space could be extremely large. So we need a strategy to explore the space efficiently. And also we want to generate queries that can execute efficiently on the video datasets. And of course, Equivocal wants to synthesize queries with high performance, such as a high F1 score. And lastly, Equivocal needs to be robust to noisy data, and the noise could come from user errors or due to ambiguous events. And as I have mentioned, Equivocal uses user-defined functions to extract semantic information from video data. And this information can be stored into these three objects, relationships, and attributes relational schema. And with this schema, we can then write any kind of relational queries. However, the issue here is that the query search space would be too large, and the query synthesis process would be very inefficient. So therefore, we want to constrain it by using SingGraphs as the data model. And in SingGraphs, nodes and edges represents objects and relationships between objects in a video frame. So here we want to find a video segment where a car arriving from the left and then passing a motorcycle at the intersection. And there are many ways to express these events. And one possible way is to use the following two SingGraphs. So in this first SingGraph on the left, there are two objects, a car and a motorcycle. And there's also a relationship connecting between those two objects, indicating that the car has to be on the left of the motorcycle. And there's also attributes applied on the car, saying that the car should be at the bottom of the scene. And the second SingGraph is similar to the first one, except that now the car moves to the right of the motorcycle. And then the first SingGraph can persist for several frames before moving on to the second SingGraph. And also the second SingGraph can proceed for several other frames as well. And we can express this spatial temporal SingGraph using the SQL queries. But now, unlike arbitrary SQL queries, there are more constraints. And this helps to reduce the query search space greatly. And after defining the data model, we can now discuss how Equivocal synthesizes queries. And let's use an example to walk through the algorithm. So Equivocal first take as inputs and video dataset. And also the video needs to include a few initial examples. And also assume that the user comes with 5 user-defined functions, and the functions can detect cars, motorcycles, and also identify relationships such as an object is on the left of another object. And the system also has some hyperparameters, and I will explain them later. So Equivocal starts with the empty query. And in the first query, we expand Q0 by adding one more predicate to it, using the user-defined functions that the user has provided. And this will give us 5 new queries, Q1 to Q5. And notice here that Equivocal synthesize queries over a compact notation rather than over SQL queries directly. And this is to help the query synthesis focus on the logics of the queries. And then we can compute the F1 score of each query using the current label datasets. And in the first iteration, that would be the initial examples that the user has provided. So to summarize, Equivocal doesn't synthesize arbitrary queries. It limits the query search by using SingGraphs, and it expands queries by adding one more constraint to existing ones. And then we could determine which query is the best using the label datasets and looking at the F1 score. However, the issue is that the initial example set is very small, so the F1 score of each query would be very inaccurate. Therefore, our system will ask for more labels to further reduce this uncertainty. It uses a disagreement-based active learning method to select the most informative segments that helps differentiate between those candidate queries. And then we can update the score of each candidate query by using the updated label sets. So Equivocal uses active learning and picks video segments that best differentiate candidate queries. And before moving on to the next iteration, Equivocal uses beam search to only expand a small set of queries with the highest F1 score, and then it will prune out the rest. So the user has set the hyperparameter BW to 2, And in this case, we will retain the top two queries, Q1 and Q3, and we will pronounce the other queries. So equivocal prunes search paths using beam search. At the end of each iteration, equivocal will maintain a list of top K queries list it has seen so far. And in this example, K is set to 1, so we add Q1 to the top K query list. And in the second iteration, we expand Q1 and Q3 that we have obtained that we have retained from the last iteration by adding one more predicate to each of them. And we follow the same pattern and repeat this process until the system reaches the boundary of the search path. And equivocal will return the top K queries list as the final result, which is Qi in our example. And our algorithm, as I have mentioned, synthesize queries using our compact query notation. And in order to execute them over videos, we have to translate them into SQL queries and then execute them in using a relational engine. And in our prototype, we use Postgres. A naive translation of this query will lead to a recursive query that are very expensive to execute. So equivocal comes with a set of important optimizations. And for more details, please see our paper. We evaluate equivocal on a synthetic dataset of moving objects and also on a real-world dataset of traffic videos. We also conduct a user study to show the performance of real users using our system. And in this presentation, I will only show some results on the synthetic datasets, but you can find the full results in our paper. So we first compare equivocal against baselines on trajectories videos, trajectory queries. And these queries involve trajectories of only two objects. And these kind of queries are supported by one of the baseline systems. So for baselines, we compare against PathSQL. This is a query by example system designed for relational data. It synthesizes arbitrary queries over smaller tables, but it's not designed for the video scale data. And for Quiver, it synthesizes queries for object trajectories over videos. And this table shows the query synthesis time for each method in order to achieve at least 0.9 F1 scores. And we compare with multiple queries of different complexities, and we write these queries manually. And as you can see, equivocal is much faster than the baseline systems. And we also find that PathSQL only works well for smaller tables. So in this case, it cannot even synthesize any queries successfully. We further like downsample each trajectory by keeping every 4 frames. That leads to this like simplified setting. But even under this setting, our system is still faster, or at least as close as the other two baselines. And we then move on to scene graph queries. And these queries are more complex than the trajectory queries, as they involve more objects and more relationships. And both baselines fail to support such queries, so we only evaluate on equivocal. And this figure shows the F1 score of equivocal for queries with different complexities. And for each of them, we also show the F1 score under different budgets, which is the total number of labels that the user has provided, including initial examples and additional ones we collected using active learning. And the main takeaway here is that equivocal can synthesize high quality queries within a reasonable budget, even for complex queries. In conclusion, we propose a new system called equivocal. It synthesizes compositional queries from user examples, and it achieves the goals by modeling compositional events as spatial temporal scene graphs. It explores query search space using results of executing intermediate queries and by using beam search. It uses active learning to reduce user efforts. And lastly, it generates efficient SQL queries to reduce computational efforts.